A contractor leaves on Friday. Their public key was copied to 37 servers over 2 years. Some by Ansible, some by hand, some during an outage nobody documented. Monday morning, the security question is simple. Where is that key still valid? If your answer is brep every authorized keys file and hope you found every account, you do not have access control. You have archaeology. SSH Certificate Authentication fixes that model. Not by replacing SSH keys, but by stopping the endless copying of user keys to every server. An SSH user certificate is a signed statement about a normal SSH public key. Alice still has her private key. She proves possession of it during login, just like ordinary public key authentication. The difference is that a certificate authority, your SSH user CA, signs Alice's public key and says, this key may log in as these principals, for this time window, with this identity string. Servers do not need Alice's public key and authorized keys anymore. They only need the public key of the CA. That is the scale win. One trusted CA key on the fleet, short-lived signed user keys for people and automation. Mechanically, the client offers two things, the user key and the matching certificate file. OpenSSH finds it automatically when it is named like IDED25519-cert.pub, next to IDED25519. The server checks that the certificate signature chains to a CA listed in TrustedUserCAKeys. Then it checks time, not before, not after. Then it checks principals. With the basic configuration, the Unix account being requested must appear in the certs principal list. So if Alice runs SSH deploy at host, the certificate needs deploy as a principal. The local account still exists, file permissions still apply, and PAM or other account policy can still run. Walk the lines. First, create an ED25519 CA key named user CA. In production, that private key is guarded tightly and normally not kept on ordinary servers. Next, copy only userca.pub to the server, commonly under /etc/ssh, owned by root and readable, mode 0644. Then create a small sshd config drop-in. The directive is TrustedUserCAKeys, followed by the path to the CA public key. That tells sshd which user certificates to trust. The signing command uses ssh-keygen with -s for the CA key, -I for the certificate identity, -n for principals, and -V for validity. This example signs your public key for principal deploy for 8 hours. Here is a clean pattern. Your fleet has a service account named deploy on application servers. Instead of placing every engineer's public key into deploy's authorized keys, you install one file everywhere, etc ssh userca.pub. Your config management writes the TrustedUserCAKeys line and reloads sshd after sshd-t passes. At the start of a shift, Alice authenticates to your internal approval process, and that process signs her existing public key with principal deploy and validity plus 8 hours. She receives IDED25519cert.pub. She runs SSH deploy at APA1. The server sees a trusted CA signature, sees deploy in the principals, sees the cert is current, and allows the login. The CA private key is the dangerous part. Treat it like a production root of trust, offline if possible, locked down, audited, and never copied to the fleet. A stolen user CA can mint logins anywhere that trusts it. Principals are not decorative labels. They decide what names the cert can log in as. Do not sign broad principals like root casually. Expiry is built in, which gives you automatic revocation at the end of the window. But it depends on sane clocks, so run NTP. If you must kill a certificate before expiry, use a revocation list with revoked keys and an open SSH KRL, not just wishful thinking. SSH certificates sit after basic key hygiene and before larger access systems. You still need strong private key protection, agent discipline, and sane SSHD policy. Certs solve the distribution problem. No more per-server public key copying for every person. They also connect nicely to bastions, approval workflows, hardware-backed keys, and forced commands for automation accounts. The certificate identity from -I can appear in logs, which helps investigations when you choose useful IDs like ticket numbers or usernames. In the advanced tier, this is the turning point from server-by-server access files to centrally issued, time-bounded access. Try this only on your own lab VM. Create a local username deploy. Generate a lab CA key. Copy only the CA public key into etc ssh-userca.pub and add the TrustedUserCAKeys line in a drop-in file. Test config with sshd-t, then reload the service. On some Debian and Ubuntu systems, the service unit is SSH instead of sshd, so use the name your system has. Now sign your normal public key with principal deploy and a short validity, maybe 5 minutes. Log in as deploy. Then wait until it expires and try again. That failure is the feature. Access aged out without editing authorized keys.
Recap in 3 beats.
First, SSH Certificate Authentication keeps user private keys but replaces authorized key Sprawl with one trusted CA public key on each server. Second, principals are the authorization names inside the certificate. For the simple case, they must match the account being accessed. Third, validity is part of the certificate, so short-lived access expires automatically, with KRLs available when you need early revocation. Tomorrow we keep building the advanced SSH toolkit with another practical administration and defense topic. New SSH episode daily on this channel, from zero to expert. Also check the daily ranked CVE brief for the vulnerabilities that actually deserve administrator attention.